Hey, what's up, guys? So, today we're going to be discussing the Lagrangian approach. Okay, so the Lagrangian approach is an energy approach. So, it really relies on conservation of energy. So, it makes the assumption that the systems are, it's a conservative system, okay, where you're not actively losing energy or losing work out of it. So I'll actually show you how do we account for this. But yeah, so the beauty about this approach is that it allows us to skip all the vector work. So if you're like me, you know vectors are ridiculous, especially when you get into a big strength matrix trying to calculate some inertia somewhere. You just start adding up a lot of matrices. The beauty is MATLAB will do all that for you, but for hand calculation, right? This is an amazing technique that helps you to do things real quick. It doesn't really act very well when it comes to dampening and friction and all that, but we shall explore this right now. All right. So let's go about this, right? So the equation is L equal to the sum of t's minus the sum of u's. T being the kinetic energy and the u's being the potential energy. Okay, so for this to work, right, how Lagrangian equations work is that, like I said, they assume that it's a conservative system, which means, right, if we would actually write that, it means that d over dt of the partial L with respect to not omega dot, x dot, right, or whatever, however you want to portray your function, right, displacement function, minus partial L over partial x equal 0, right? Conservative system. So obviously the ways to get around that is you're basically getting forces from work. That's what you're doing right here in that term. So what you're doing here is that you can put your forcing functions and your friction forces and all this stuff. Okay, so let's talk. Okay, so how do I express that, right? So we mainly see some components here, right? Yeah, so here are my main components. Right? My main components is M. So my kinetic energy for this guy is going to be half M times V dot squared. Again, X, my displacement function, squared. X dot is the speed, right? Squared. And then my kinetic energy for the spring is the energy it holds, which is half of kx squared. Okay. This guy here is not going to be accounted for in this equation. It's going to be accounted for here when I try to, understand where did I lose my energy. So this one will stay as is, Cx dot. And then over here, when I'm talking gravity effect, I'm really talking like potential energy, right? So your potential energy is your equation for potential energy, mgh, or mgx. Okay? All right. Let's jump in here. All right, so here's an example, right, of a system. So first thing I do is define what's my degrees of freedom. So I say, okay, how many rigid bodies do I have? I don't have any. Well, how many planar bodies do I have? I have one planar body. How many constraints do I have? Well, that system is not moving up and down and it's not rotating, so I have 2 constraints. So this turns out to be a 1 degree of freedom system. So predictable. All right, so 1 degree of freedom system, which means I need 1 equation. Just out of good practice as an engineer, you always want to have a free body diagram. So my free body diagram says I have mg here, I have my normal force here, I have my forcing function here. I have my f of c here, and I have my f of k here. Okay, great. So how will I write my terms over here? So my L is equal to the kinetic energy. Again, this is my direction. So you take a direction and you stick to it. So my direction here says the kinetic energy of the mass, which is half mv, right? Another way to write that is half mx dot squared minus, because the spring will be actually absorbing that energy as well, right? So because I'll be putting energy into that spring because it's in the motion against. So half kx squared, okay? Minus, what are my potential energy? My potential energy is just m times g times nothing, because I have no movement in that direction, so my potential energy is just, yeah, figured I'd play a little bit. All right, so my partial L over partial x dot is, now remember, this partial here is not differentiating with respect to time, which means this guy here is a constant, so it goes to 0, and this guy here, right, is basically half times 2 times mx dot. That's what that is, right? So we end up with mx dot. Now, when we take that and differentiate it with respect to time, right? Because remember the equation? The equation is d over dt of dl partial x dot minus partial L partial x equal to 0 in a conservatory mode. All right, so this term here is that term here. So this is going to equal to differentiating this with respect to time. So that's just going to be a simple mx dot double dot. So looking familiar? All right, let's move on. Partial L over partial x is going to equal, again, this is going to be a constant, so I'm going to only have this term here, which is going to be my negative half times 2, which is 1, and then kx, right? So when I write this, right, I'm going to write is equal to, again, I don't want to write the 0 here, is equal to mx double dot minus kx, right, equal to, remember, the system is not being conserved. I have an f of t acting on it, and then I have a friction force. So it's going to be a minus, oh, sorry, this is a plus here because it's a minus minus. And then a minus, excuse me, a minus c dot, cx, not c dot, cx dot, okay? So this looks familiar, right? This is your typical first degree equation of motion. Mx double dot plus cx dot plus kx equal f of t. Okay, let's try and move something a little more complicated. All right, for time's sake here, let's go over this. Degree of freedom. How many times? Well, I don't have any rigid bodies. I have 2 planar bodies, right? And then I have 2 constraints on this because there's no movement in this direction and there's no rotation. So 2 per each, which is 4, which gives me 2 degrees of freedom. Okay, let's pick the first body. First body, M1. What do I have? I have gravity acting this way, right? I have my f of k, and that's basically it. And I am defined, x1 is down. So, just looking at this term over here, right? I have L equal to half of m x dot squared, right? Plus, can you see that? Because, sorry, minus, because it's still against it, right? I'm stretching the string. Minus half of k x squared. Okay, and then I have potential energy in this situation, so it's going to be minus m1, so this is all 1, m1 g x1. Okay, so this is my equation here. Now let's do this with respect to x. This is going to equal to, I have my negative kx, k1 x1, and then I have this term here, x disappears, so minus m1 g. So that's my first term. My second term is going to be L over x dot, which is going to equal to m1 x dot, and then I take the derivative with respect to time to that. So that will give me here m1 x double dot 1. This is 1. So when I put this together, my first equation of motion is going to be m1 x double dot 1 plus, minus, right? This guy's here, which is minus k1 x1 minus m1 g, right? So that's going to be equal to 0. So that's my first equation of motion. All right, let's do the second one. So I have my body here going up this way this time, right? I have m2, some string, I have fk of 2, and then I have gravity acting down. Right? So my equation for m2, this is m1, is going to equal to, again, now I'm going up, so half of mx dot squared plus, because I'm going up, remember, half of k2 x2 squared minus my potential energy, which is m1 m2 g x2. Okay, so let us differentiate that. m2 for x dot, right? I'm gonna have my m2 x dot, and then take that with respect to time, right? So just m2 over x dot is going to equal to m2 x2 double dot, right? Your typical term. And then let's take with respect to x, it's going to give us k2 x2, right, minus m2g. Now putting those guys together, I have m2 x double dot minus k2 x2 minus m2g equal to 0. And that is my second equation of motion. So it is that simple, okay? Nothing too complicated about it. You just have to be systematic. So if I have to summarize, what do we need to do here, right? What we need to do is, like we mentioned in the last time, right? Number 1, find out how many degrees of freedom do I have. Number 2, find out the kinetic energy, right? For everybody. So I guess I would say segregate the body, right? Segregate it. Segregate the body into its free body diagrams and then do an equation of motion for each of them, right? And however they're necessary. And then after that, you apply the equation, which is d over dt of partial L over partial x dot minus partial L over partial x equals 0. Conservative order. And then you add your viscous damping and forcing. Your losses, basically. Losses or gains, like stuff that are not related to the system that's being conserved. All right. Well, if you have any questions, please let me know, and I will modify this for you. So, thank you very much for watching.